Hello, wonderful Patriots. Good morning or afternoon or whatever time it is. Welcome back to the Mathnasium. We've got an exciting video for you today. This is 6-3 Day 1, Binomial Random Variables. I'm really excited to teach this lesson. However, I wish I was here in person. This is one of my favorite ones to teach for the whole year. So hopefully this is an exciting video. I put a lot of work into it. So sit back and grab a pencil and paper. You feel free to take some notes. This video will be, immortalized on the internet and whatnot, but you may need to pause because I have a lot of it pre-written because I know my computer can lag when I'm recording sometimes. So let's get started. So start off story time. 2005, Memphis trailed Louisville, as some people say, by 2 points, 73-75, at the buzzer of the game. So 0 seconds left on the clock. And Memphis, this guy right here, his name is Darius Washington. He got fouled on a 3-point shot that he missed. So you can foul and make and still get your shots or something along those lines. But he was fouled and he missed the shot. So since that was a 3-point shot and they determined it was a 3-point shot, he gets 3 free throws. Now, this is a very interesting situation. He's a 72% free throw shooter, and we're going to assume in this case that, if he makes these free throws, it's not going to determine whether he makes or misses on the next shots. But here's the situation. We have a couple things that can happen to Darius here that are pretty interesting. This can go really 3 different ways. Okay, so 73-75, they're down. There's no time left on the clock, so his shots, this can result in 3 possible outcomes. Okay? Sorry, what was that? Weird. Okay. They can result in 3 possible outcomes. Those outcomes being, so we're gonna define a random variable as x equals the number of free throws made by Darius. This is a binomial setting, and we're going to talk about what that means in just a minute, but let's first do some math, and so you can see the math, and then we can identify it, and we'll move on from there. This is a binomial random variable. What is every possible value of x? That is, what is every possible number of free throws that Darius can make in this situation? Well, he has 3 spots. So there are 4 values. Darius can step up to the free throw line, and he can shoot 3 free throws and miss all 3. If in that case, Memphis would lose the game because the score would still be 73-75. He can make 1 shot, which would bring the score to 74-75, and then Memphis would lose. He could make 2 shots, which would bring the score to 75-75, and then it would be a tie game, and then they could go into overtime and have the chance to win. Okay. Or he can make all 3, and if he makes all 3, the game is over, Memphis wins, and they go on to the NCAA championship. So this is high stakes, okay? High stakes, and really, I mean, you got pro ball teams watching these guys. I don't know what happened to him after this, but it's an interesting situation. So the probability that he makes a shot is 72%. The probability that he misses then is 28%. So this is every possible, there are 4 possible values of x. I want to calculate the probability of each one. So let's do that. And we have the skills to be able to do this, so just work along with me. What is the probability that he misses all of his shots and Memphis loses? Well, this is going to look like, probability-wise, we would say that's the probability x equals 0, which is the probability of a miss, and a miss. What's the probability of a miss? It's 0.28. So we're assuming each one is independent of the next. So this is going to be 0.28 times 0.28 times 0.28. Oh my gosh, little thing. Right here. Which is 0.28 to the 3rd. And if you sit and multiply that out, 0.28 times 0.28, you get a probability of about rounded 0.022. So there is a 2.2% chance that he would miss all 3 shots. And we're making some assumptions here. These assumptions are, he's not nervous, which he is. He has the same shooting ability now as he would in a regular game. Not under these circumstances, which is probably not true. But anyways, we're gonna go off his sports card here. There's situation 1. We take all these and we multiply them, okay? Now, we can't simply, when he goes to make one shot, we can't simply say, hey, it's going to be 0.72 times 0.28 times 0.28. The reason we can't do that is because there's 3 ways for him to make a shot, okay? He can, oh my gosh, smart notebook. Why don't I have a computer that is fast-ish? Okay, there we go. So he can make the first shot and then miss the second 2 shots. He can miss the first shot, then make the make the first one, miss the second 2, miss the first one, make the second one, miss the third one, right? He can miss the first 2 and then make the last one. So these are all the options for Darius if he was going to make one shot, and each one is independent. And each of these has their own probability. The probability that he makes the first is 0.72 times 0.28, so make, miss, miss. And then this is going to be miss, make, miss. The success, the 0.72, is in the middle, and here it's on the end. Now, all of these 3 things are essentially the same number, right? It's 0.72 times 0.28 times 0.28, and we can multiply in any order, so we can shuffle them around and write this as 0.72 times 0.28 to the second. And there are 3 of those, so when we add them together, it's really 3 times that number. So 3 times 0.72 times 0.28 squared is 1.169 rounded, which is 16.9%. So there is a 16.9% chance that he makes one. There's a 2% chance that he makes none, which means he's got a good chance here of either tying the game or winning for Memphis. Okay, make one shot. Turns out there are also 3 ways. Oh my gosh, computer. Lagosaurus here. If my computer was a dinosaur, that's what I would name it. All right. There are 3 ways to make 2 shots. That is make, miss, make, miss, make, and miss, make. And similar to the last math, there's now, instead of having 2 0.28s in each calculation, there's 2.72. So that's a make, and a miss, the probability of that happening, plus a make, a miss, and a make, plus a miss, a make, and a make. And this time, 0.72 is to the second power. 0.72 is to the second power. And there are 3 of those, so when you add those up, it's 3 times 0.72 squared times 0.28. So there is a 43.5% chance that that Darius here is going to make 2 shots, which will send them into a tie game and send them into overtime with the chance to win. So this is the highest one we've seen so far, which is pretty exciting. And then, of course, the last situation is he makes all 3 shots, which is make, which is 0.72 times 0.72 times 0.72, which is 37.3. So there's a pretty good chance he could make all 3 and Memphis could win. So we have all 3 of these. This makes up our probability distribution for, we have every value, and we have all of those values probabilities. We now have the full probability distribution for our random variable x, which is the number of shots that Darius will make in this situation, assuming the shots are independent of each other, and he's not nervous, and he has his actual 72% stat. So yeah, not likely, but still. So we have all of those probabilities, which is pretty exciting. Now, you might be wondering, is there some sort of a pattern to this? Well, yes, there is, and we're going to get to that in a little bit, but it is very repetitive. And you'll see, like this one, you know, we didn't have a number out front here. Here we had the number 3 out front before we multiplied. Here we had the number 3 out front before we multiplied. And here we had the number 1. It turns out that those correspond to specifically a binomial situation, binomial expansion, and Pascal's triangle. And we'll get to that towards the end of the lesson. I'm going to just comment on that a little bit. So working from here, let me make sure I've covered all my bases. we can start doing calculations, like what's the probability that they lose? Well, that would be the probability of x equals 1 plus the probability of x equals 0, which is 19.1%. There's a 19.1% chance that they lose. What's the probability that they win? Well, that would just be x equals 3. And what's the probability that they tie? Would be 43.5%. So we can talk about those things. Okay, cool. So we've done this thing. Great. That's fantastic. This is a lot of work. We don't want to have to do this big, long string of calculations for every problem. Mr. Schlegel, is there a faster way? Yes, there is. But first, we need to identify what the binomial setting is. We can only use the trick that I'm about to teach you to make this faster if we have established it as a binomial setting. So, is a random variable binomial? We use the acronym BINS. This is like SOC V and the other ones that I've taught you. Is it a binomial setting? So the BINS stands for, B stands for binary. Is the outcome of each trial either success or failure? In the case of Darius, each trial was each shot, and he could either make it or miss it. It's important to note that you don't have to have, like, it doesn't have to be only two options, if that makes sense, right? You could have, like, for example, so anything that's countable as a success or failure. So, like, you could be like, a student in my class stole my wallet and I have to guess who it is, right? There's lots of possible students and I could guess correctly or guess incorrectly. So either a success or failure. By the way, do you know who has my wallet? I still haven't found it. Keep an eye out for it. There's like at least 50 cents in there. Are the trials independent? Okay, trials must be independent from one another for it to be a binomial setting. What does this mean? Knowing the outcome of one trial doesn't tell us anything about the outcome of another. In this case, if Darius misses a shot, that's not going to change the probability of him making or missing the next shot. Now, I think you could argue that that may not be the case under the pressure, but we're going to assume for the sake of our calculations that it was a binomial setting, that they were independent. And there probably were. Who knows? And the number. Is there a fixed number of trials in advance? In this case with Darius, yes, there was. We knew that Darius was going to shoot 3 free throws, and that was it. So it is confined to 3. There is a fixed number of trials in our setting. That is a requirement for binomial. So trials, we have, there can only be success or failure. That's what you're measuring, success or failure. Trials must be independent of one another. There's a fixed number of trials before you begin, and each trial must have the same probability of success. Similar to independent, but yeah, so there we go. Here's the quick way to do it. This is exciting. So for any this is what you need to know, and I think that this is on your formula sheet. I don't have one next to me, but I think it is on your formula sheet. For any binomial random variable x, where x is the number of trials, or sorry, where n is the number of trials that are being determined, p is the probability of success of each trial, and k is the number of successes, then we have that the probability that x equals k equals n choose k, so this is combinations, okay, combinations times p to the k times 1 minus p to the n minus k. So let's see if we can do that for Darius's situation. Apparently not. All right, I'm going to pause the video and then write this, and then it'll pop back up. So hold on. All right, so we're back here. I got it recorded. So in this case, we know that the number of trials n is 3 for Darius' situation. So we would do 3 choose 2, and then 3 choose 2. Now, you can use, my pen is taking forever to record. You can use, I think it was 5-3 day 2 when we learned about combinations. So you can use that little trick, which is, if you're going to do 3 choose 2, it is, you can use your calculator to do that, or you can use the formula from that day, which I think is like n factorial over k factorial times n minus k factorial or something along those lines. So use that formula that is given to you for combinations. I want to remind everybody that combinations can be written multiple ways. So let me pause the video right now and just write it the other way so you're familiar with that as well. Okay, so you can see down here, I've written it the way that the AP exam questions are going to show it. They're going to show it like this, not like that. Your calculator shows it like this. Lots of people write it like this in mathematics, but it's also written like this. This means combinations or choose notation where order does not matter, basically, which is interesting. Okay, super. So we know how to make probability calculations now, and we're going to do some practice here in just a minute. I'm going to show you how to do this the long way. So this is the fast way. The long way is what we did with Darius. This is kind of like the medium fast way to do it by hand and show our work. And there's even a faster way with your calculator to check your work, and I'll get to that too. So let's keep moving. You roll a 10-sided die. 10-sided die has 0 to 9 on it, and you roll it 6 times. Let's assume you're playing Dungeons and Dragons or some board game here, right? If you roll a 9, you get a critical hit on your enemy. Find the probability that H equals 4. All right? You guys give this a shot. See if you can do it with the situation at hand. And then, yeah, I'll unpause the video and we'll go to work and you'll see it there. So here we go. Give it a try. Pause the video or pause this video and then give it a try as a class. Okay, here's the start. Here's the setup. It should be 6, choose 4. You're looking for 4 critical. You're rolling the die 6 times. You want 4 9s in some order, right? 4 9s, and so that would be 4 critical hits, and then you're going to have 2 misses. So what choose tells us, it tells us the number of different ways that we can make that happen. The number of different ways that we can have 4 critical hits and 2 misses, so you're multiplying that, okay, together. So you guys do this calculation by hand really quickly, and then I'll unpause the video with the answer. All right, so here's what you should have. 6 choose 4 is 6 factorial over 4 factorial, which will be, 4 down is going to cancel, so it'll be 6 times 5, which is 30, divided by 2 times 1, which is 15, and you multiply those two out to get, there's a really like a 0.1 chance that happens. If you roll a 10-sided die 6 times and you're looking for 4 critical hits, then it's going to happen 0.1% of the time. So not very good. Not going to happen very often. All right, so now we're going to run through some situations. We can't use the binomial setting until we argue that it is indeed a binomial setting. We just assumed it for this. I didn't tell you, make you check or anything. So we're going to run through using our BINS acronym or mnemonic, and we're going to check each of these situations and determine if it's a binomial setting. Let's go for it. You shuffle a standard deck of 52 playing cards. You turn over the first 10 cards one at a time. Record the number of aces that you observe. Okay, so is this a binomial setting? Let's think about this. Is it defined a probability of success and a probability of failure? Yes. Is there an ace? Getting an ace would be a success. Not getting an ace is considered a failure. So yes, we do have a binary setting. So that's the B from BINS, okay? Are these things, is each trial independent of the one previous? Now, let's think about this for a minute. Since we are turning over the first 10 cards of the deck and we're recording the number of aces, the trials are not independent because you could draw an ace on the first card, and then the probability of getting an ace on the second card is now lower. So since the probability of getting an ace changes, right? Even if you don't get an ace, right? If you flip over the first card and you don't get an ace, now the probability of getting an ace is higher because there's one less card in the deck. So are the trials independent here? The answer is no. So since the trials, so no, this is not a binomial setting, and we can say, this is, I'm gonna have to write it because my thing is laggy. I'm gonna pause it again. I'll write it out and then we'll come back. Okay, so since we are sampling without replacement, the trials are not independent, and that means that this is not a binomial setting. So this fails the independence requirement, so we can't do the calculations with the formula that I gave you. Okay, how about this one? Shuffle a deck of cards, turn over the top card, put the card back in the deck, shuffle again, repeat this process until you get an ace. Count the number of cards you turn over. Okay, is there a success? Is it a binary situation? Let's think. Yes, you can see an ace or you cannot see an ace, so there is success and failure. Are they independent? Yes, they are independent because we are putting the cards back in and shuffling each time. And we're going to keep doing that until we get an ace, and then we're going to stop. Okay? The reason that this is not a binomial setting is because there is not a fixed number of trials. We could sit here, theoretically, all day long, drawing a card, not getting an ace, shuffling, drawing a card, not getting an ace, and we could be there, in theory, all day and never draw an ace, even though that's unlikely. We would get one eventually, but it would take quite a while. So this fails the fixed number, the n of bins, right? This fails the fixed number of trials. There is not a fixed number of trials here. We could be doing trials indefinitely. So this is not a binomial setting because there is not a fixed number of trials. And there you have it, folks. If any of those categories fail, we can't use the equation that I gave you previously. Let's move on to another one. Whoops. Sorry, I did that again. You take 10-question multiple choice quiz where each question has 5 options. Okay, let's think about this. For each question, is there a clear success failure? Yeah, you can either get the question right, you can get the question wrong. If you are randomly guessing, okay, assume we're randomly guessing on each question, what is the probability, assuming we're randomly guessing, if I guess on the first one, does that change my probability of guessing right on the second one? The answer is no. So we know that these guesses are independent from one another. Is it a fixed number of trials? Yes. There are only 10 questions, so there are 10 chances for success or failure. Lastly, do they all have the same probability? Yes, because they all have 5 options. So this is a binomial setting, so we can proceed. We can proceed with the binomial setting, and I'm going to show you kind of a quick way to do this. We're almost done. I can do this by hand. I'll do it by hand, but I want to show you the quick way to do this as well. So you guys give it a shot. I'm going to pause. You pause the video. See if you can try to get this one. Find the probability you get 6 correct. If you get it, great. And then we're going to move on to these other 2, which are a little bit harder. So, all right, I'm going to write it out. All right, everybody, you should have a probability of 0.5% or 0.0055 probability. So the likelihood of getting 6 questions correct is less than 1%. Less than 1%. Okay. So how do we do these with our calculator and not have to use this formula? Well, it turns out there's a really easy way to do it. And just like normal CDF, there is a calculator command. And here's the big rule. This is one you need to write down. Anytime you're using a binomial setting and you have exactly one outcome you're looking for, so 6 correct, right? We're just looking for 6 correct. We can use binomial PDF. Anytime we are looking for a range, we can use binomial CDF. Now, binomial CDF takes CDF stands for cumulative distribution function. So cumulative means it adds stuff up. So if you want to calculate the probability that you get 6 or more for the thing down below, we're going to have to use CDF. So anytime there's a range of values with binomial, you use CDF, binomial CDF. Anytime you have a single value, you're going to use binomial PDF. Okay, so let's now, I'm going to kind of set these up and I'm going to show you how to do them, and then you can try the last one. All right, let's take a look at these two problems. So if you use binomial PDF on your calculator, the things that it asks for are, you have to go to second distributions, and you scroll all the way down. Binomial PDF and CDF ask for the same things. PDF asks for a single value, so you plug in the number of trials, which is 10. You're going to plug in the probability of success is 0.2 because there's 5 options, and we're looking for the probability. So this is PDF for just 6, so then it just gives you the probability of 6. Now, if you wanted to do 6 or more correct, you could do binomial PDF of 7 plus binomial PDF of 8 plus binomial PDF of 9 plus binomial PDF of 10. You can do all that, or you can do CDF. And what CDF does is it gives you everything down to the left, including the value that you said. So basically what I did here is I said, well, instead of doing CDF reads to the left, right? So it's going to do, if I do binomial CDF of 6, it does the probability of 6 plus the probability of 5 plus the probability of 4 plus 3 plus 2 plus 1. So we do 1 minus the probability that x is less than 7, which is 1 minus binomial CDF 10, 0.2, and 6. Okay, so it's cumulative, which means it adds up to the left, just like table A. So it's going to add up the probability of 0, 1, 2, 3, 4, 5, and 6, and we're subtracting that from 1 to get the probability that you get more than 6 correct. And it ends up being a value. I'm going to write it. We'll see if Smart Notebook likes this or not. Nope. I'm going to pause the video. All right, so we get here the probability of 0.000864, probability that you get 6 or more correct on a test. So the probability of passing a 10-question multiple choice randomly is very slim. Amazing. Okay. So how would you get between 3 and 6 correct? Let's say for this, 3 and 6 are included. So 3 and 6 are included. How would you do that calculation? You guys give it a shot, and then I'll put the answer on the board in just a sec. Pause the video. All right, guys, so you should have a probability of 32.1%. You would do binomial CDF, which is adding up all the probabilities from 6 all the way down. So the likelihood of getting 6 questions plus 5 plus 4 plus 3 plus 2 plus 1 plus 0, all the way down to 0. And then you're going to subtract the binomial CDF. This is just like with normal distributions. We're subtracting, and I've changed it to 3, 4, 5, or 6 correct. You may have misinterpreted that and got it wrong because it wasn't clear, so I apologize. But 3, 4, 5, or 6 correct, so you would subtract the 2, the 1, and the 0, which is what this binomial CDF does, and we get that 32%. All right, that's it for the video. I wanted to do one last quick comment on Pascal's triangle, and that's right here. So how does this relate to what we're doing? Well, I don't know if you remember with the Darius Washington example, but we had the coefficients on our 3 situations, that is having 0 makes, 1 make, 2 makes, and 3 makes. The coefficients on those were 1, 3, 3, and 1. Well, that corresponds to the 4th row of Pascal's triangle because there were 3 trials in the simulation, right? He was taking 3 shots, so that's 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So if you want to figure out what the coefficients of the situation are in any situation, Let's say if Darius Washington, for example, were to take 4 shots instead of 3, which is not the situation, and you wanted to know the coefficient, or you wanted to know what, for example, 4 choose 2 is, or 5 choose 2, you can calculate those using Pascal's triangle, which is you start with a 1, 1's on the outside, and then you add the 2 things previous. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 3 is 6, 1 plus 4 is 5, so on and so forth. And it correlates directly to probability and choose notation. So that's basically it. Your assignment's posted. Hope you enjoyed the video. It was a lot of fun and to make. Sorry for slamming the desk. Hope you have a great day, and we'll go over this more when I come back. Please watch the whole video. We got to stay on track here, so peace out. Thanks for watching.